questions for homework last night. 2 questions, sorry, for homework last night. Worksheet number 4, questions 2 and 3. I want to do question number 3 here right now. It says a 4-kilogram ball traveling north with a momentum of 11.2, with a momentum of 11.2, not a velocity, a momentum of 11.2, collides with a 6-kilogram ball traveling west with a momentum of 18. They stick together, head off as one. What's the momentum of the combined mass? What's the velocity of the combined masses? And what's the momentum of the system before this collision even took place? Seems like there's a lot that we're asked to solve for here. The good news is there's 3 things to find, but once you find the first thing, there's not very much work to find the last 2 things. Let's set this up here. Let's draw it out. We have one object that's going to the north, and we have another one that's going to the west, object number 2. Now, where is this wreckage going to go? These 2 balls going to go after they stick together and head off as one? Yeah, somewhere north. Don't say northwest, because that infers a 45-degree angle, northwest, north and west somewhere, right? So I know what you meant by it, but somewhere in that general vicinity. What angle exactly, we don't know. That's for us to figure out here. All right, we have a mass here for object number 1 of 4.00 kilograms, but we have a momentum this time, not a velocity, but a momentum of 11.2 kilograms meters per second. That's a little bit different. We used to be given the velocity. Number 2 is 6 kilograms, and its momentum is 18 kilograms meters per second. Okay, we know what to do with this, right? Like, just because we're given momentum here as opposed to velocity, doesn't make any difference in the way that you start this question. Okay, everybody, regardless of whether you were thrown off guard by the momentum that we were given or not, everybody knows where to start this, right? X and Y components. And what do you do within the X and Y's? Pi is equal to PF. Now, at this point, people might have been like, what do I do here? M1, V1, I don't know what V1 is. What some people did, I think, is said, well, look, I know the mass, and I know the momentum. Could I not find the velocities by using P is equal to M times V? And then I could say M1, V1, I plus so on, right? Could you do that? Of course you could. If you find the velocity right here, this question just turns into any other question. Question like number 1 or question number 2. But there's a shortcut here. For the X component of object number 1, what's its momentum? The X component of this 11.2, how much of this is X component? 0, right. I don't need to find the velocity here by dividing by mass and then turn around and multiply it by mass again here to get the momentum that I'm already given. Like, this is usually M2 V2I, right? But we know what M2 V2I is. We're given that in this question. If you want to find the velocity and by dividing by mass and then turn around and multiply by mass again to find the momentum again and get 18, just like we have right here, go ahead and do that. But it's a lot of work that's not necessary where you have the momentum given to us. This is meant to be an easier question, not a harder question. PF, the final momentum is, let's call it PF. Okay, so the final momentum X component is negative 18. You could have said M total times VF and then solve for VF instead of PF. Whatever, that's fine. I found final momentum, you found final velocity, doesn't really matter. Let's do the Y component though. Pi is equal to PF. This time we're going to say 11.2 for the first object, because it's all Y component, plus 0 for the Y component of the second one, equals the final momentum, M total times VF, or just PF. So what are we saying here? Look, the initial momentum of this system, X component, there's only one, it was 18. What's the final momentum X component? 18. The initial momentum y component was, well, there's only one with a y component. It was 11.2. What's the final y component? 11.2. Same as the initial was, right? Let's combine these. I get 18 this way, and I get 11.2 this way. Now, this is P, right? Not V, because I'm doing the Pythagorean theorem with momentum as opposed to velocity. If you found velocities, you could find the hypotenuse of the velocities. I'm just doing it with momentum instead, that's all. So P is the square root of 11.2 squared plus 18 squared, which gives me a value of 21.2 kilograms meters per second. And the angle there, the theta, the inverse tan function of opposite over adjacent, I'm using 11.2 over 18 for momentum, but if you had have used the velocity x, velocity y, you would have got the same angle, and it works out to be 31.9 degrees. That would be north of west. Why north of west? Well, because this vector is going north and it's going west, but the angle is measured from the west, north from the west, north of west. Does that make sense? Now you were asked to find the velocity of the combined masses. Some of you already found the velocity, right? If you did it my way, how many people did it my way, by the way? Okay, most of you did it the other way. Interesting. If you found the velocity already, then you got to go back and find the momentum. How would you do that? Who found the velocity? What'd you get? What'd you get for the velocity? Okay. What did you get for the velocity? Okay, so the velocity is 2.12. We'll now turn around and multiply 10, the total mass, by 2.12. That gives you a momentum at the same angle. What I'm going to do is rearrange it to solve for v since I have momentum. Instead of multiplying by the mass to get the momentum, I'm going to divide by the mass to get the velocity. 21.2 divided by 10 equals 2.12 meters per second. And of course, the angle is already found, 31.9 degrees north and west. Does that make sense? What about this last question? What's the momentum of this system before the collision? The momentum after is 21.2 at 31.9 degrees. The velocity after is 2.12 at 31.9 degrees. What's the momentum before? How would I go about doing that? Whew. That's a toughie, eh? I haven't shown you how to find the momentum before in one of these collisions, have I? Corey? PI equals PF. So what's the answer, Corey? 21.2 at 31.9 degrees north of west, right? That's the momentum after that we found, but it's also the momentum before because the initial momentum equals the final momentum. Is that good? So once you found the first thing, whether it was velocity or momentum, whatever you chose to do, the next part was fairly easy. We just had to use P is equal to m times v. And then the third part, which is the one that seemed the hardest, is just write down a number that you've already found. I got another example that I want to do with you now. It's example number 2 in the booklet. This is a 3 kilogram fireworks bundle of fireworks sits on a table. It explodes into 3 pieces. The first piece goes north. The second piece goes 30 degrees south of east. What's the velocity of the third piece? Where does the third piece end up going here? Let's draw our situational diagram. Remember the difference between a situational diagram and a vector diagram? My situational diagram just shows me what's going on. Here's my explosion point. I got a piece going north. I'll call this piece number 1. Its mass is 1.20 kilograms with a velocity of 120 meters per second. Then I got another one going at 30 degrees south of east. That would be down here. And that's 30 degrees south from east. 1.10 kilograms and a velocity or a speed of 100 meters per second. Is that okay so far? Where do you think the third piece is going to go? There is a little bit of guessing here on this, but the good news is if you guess wrong, it's a situational diagram. It's just to help you visualize it, right? So it's not the end of the world. If you guess wrong, where do you think it's going to go? Yeah, we know for sure it's going to go left because we have momentum to the right. It has to cancel out, right? Now, left and down, left and up. We're not really sure about that because we have momentum both up and down between objects 1 and 2. So I don't know if 3 is going to go up or down. Depends on how big the other momentum is. Yeah, you know what? I'm going to guess left and down. Could be left and up, but if I guessed wrong, it's just a little bit more difficult because I'm not visualizing it correctly, but it's not the end of the world. We got to do PI is equal to PF, but man, there's something that you should see right now, something that should stand out to you even more than PI equals PF, X and Y components. What is it? What is it, Cooey? Yes, 5 words. What are they? I don't like funny angles. We got an angle of 30 degrees here. I don't like it, so what do? Take it off to the side and get rid of it. All I want to do here is change this 100 meters per second into an X and a Y. So I'm going to do that now. Take it over here, label it as 100 meters per second. Let's label the X component right here and the Y component of it right here. And the angle is 30 degrees. You guys know how to find X and Y, right? If you use sine, cos, and tan, if you're sine, cos, tan people, that's the way that I'll do it here. Hey, or if you're sine law people, in the end, you can still find X and Y either way. I'm going to say for X, cosine 30 degrees is equal to X over 100. X is equal to 86.6, I think it's 602. Yes, 6025. And the Y component, this one's easy because it's sine 30 degrees. Y over 100. Y is equal to 50 meters per second. That make sense? I'm going to put a little box around this, not because I have to, but just because structure. That's the way I do it. If you do it the same way each time, if you have a certain structure about doing stuff, and it makes you more comfortable when you get a question on a test. Right? This is the way I do it. Put a box around it, just take it off to the side because it doesn't really form part of the main part of the question here. Now, if you want to, you don't have to do what I'm about to do, but you can if you want. What you can do is replace this 100 meters per second with this 86.6025 and this 50. And if you want, you can even erase this. You don't have to. But you know that once I resolve that funny angle vector at 100 meters per second at 30 degrees, it is dead to us. We never want to see that 100 meters per second again. Right? We've replaced it with 86 and 50. So just erase it if you want. Scratch it out if you want. Now we got to do X and Y components. Now we just go back to doing what we did for all those other questions. The initial momentum is 0. The final momentum is m1 v1f plus m2 v2f. Oh, look at this. Plus m3 v3f. Because there's 3 objects. Oh, I so wish the masses of these 3 pieces were the same. Because if they were, then I could what? Cancel, right? They're not, though. M1 is 1.2. What's V1F? Evan, what's the x component of that 120 meters per second? 0, right? So we're going to cross that off. M2 is 1.10. What's V2F? That's the one that we just got rid of, right? I'll give you a hint. It's not 100. Why? Because 100 is dead to us. It's not 100. What's V2F? X component. How much of that 100 is X? Yep. 86.6, right? Plus M3, which is, what is the third piece mass? The fireworks was 3. We had 1.2 go off one way, 1.1 go off another way. 0.7 is it? 0.7 is left for piece number 3. So we solve for V3F here. That works out to be negative 136.0896. What did I say? 0896. Yeah. Make sense? Once you get rid of this funny angle, it's just like the other questions, right? We have an 86 x component, put it in. Imagine what you're going to do now for the y component. Zero initial momentum, m1 v1f plus m2 v2f plus m3 v3f. (1.2 times what's how much of that 120 is y component? How much of that 120 is y component? No. How much of that 120 is up or down? Yes, good. 120. That didn't work very well, hey? 1.2 times 120. All right, M2. What is M2? 1.10 kilograms. What's V2F? Hey, what's the y component of that 100 meters per second? Remember that 100 meters per second that's dead to us. Colton, how much of that 100 meters per second that I just erased, so we know it's not 100, right? How much of that is y component? Yes, except we're going to make it negative because it's 50 down, right? Good. Plus M3, which is 0.70 times V3F. All right, we solve for V3F here. For the y component, it works out to be negative 127. Point 1429 meters per second. I don't really care if you color code it like I have, but you see what I'm doing with this green and blue color coding, don't you? Right? Like I had 100 meters per second. It's gone now. We're never going to use that again. I replaced it with a blue 86 and a green 50 indicating X and Y. And then you can see down here where, well, instead of putting 100 in here, I put blue for X. And instead of putting 100 in here, I put green for Y, right? Okay, that's helpful. Then color code it. You don't have to, though, obviously. Okay, how do I do this now? This is Physics 20 now, right? If I gave this to my Physics 20 students, well, actually, they couldn't do it yet, but if I gave it to last semester's Physics 20 students, they could absolutely finish this off now. If you've done 2D vector analysis, you know that you just say 136.0896, 127.1429, head to tail, right? Head to tail there. This is my vector diagram now. Oh, look at that, Parker. You guessed it was left and down. Well, you knew it was left. You guessed it was down. Sure enough, it is left and down. Solve for V, solve for theta. V is the square root of all that squared. Gives me 1.9 times 10 to the 2. And theta is the inverse tan function of opposite over adjacent. Or sine law or cosine law, whatever some of you like to do. That gives me 43 degrees. 43 degrees, what of what? I'm going south and I'm going west. My angle is measured from the south or from the west? It's touching the west, right? So we're going to say it's south from west or south of west. Or if you had it drawn it the other way, like this, you would have gotten an angle of, what would that have been? 47 degrees west of south. That would have been fine as well. Let's have a peek at worksheet number 4, questions 4 to 6 that you've been working on for the last little while here. Number 4 specifically says a 400 kilogram bomb sitting at rest on a table explodes into 3 pieces. 150 goes this way. 100 piece goes this way. What's the velocity of the third piece? Draw your situational diagram. Okay, there's my explosion point. We have one piece going to the east. We're going to call this piece number 1. Its mass is 150 kilograms, and its velocity is 150 meters per second. We got another one that's going south of west. This is piece number 2. It's 30 degrees south of west. Its mass is 100 kilograms, and its velocity is 200 meters per second. And then the third piece goes, I don't know exactly where it goes. We know it's going to go up somewhere, up and to the left, up and to the right. Not really sure. We'll guess up and to the left. Okay, there we are. We got a funny angle in here, 30 degrees. First thing we do is get rid of that. It's always what we do first. Got a funny angle. We don't like funny angles, so we get rid of it. Up here, off to the side. This is 200 meters per second. This is my x component right here. And this is my y component right here. And I can find x and y. I'm going to do that. Cosine 30 degrees is equal to x over 200. Or x is equal to, I think it was 173 or something, wasn't it? 173.205. And the y component, well, that's the opposite side, so we're going to say sine 30 degrees for that is equal to opposite over hypotenuse. That's a nice easy number, 100. Then we're going to box this off. Why? Because that's what we do. You're used to doing it a certain way, then we're more comfortable when we see this question on our test. Now, if you want to, you can draw this in over here. Like, here's my x of 173.205, and here's my y of 100. And if I want to, I can completely get rid of that 200 meters per second because it's dead to us, right? We never want to see that again, this 200 meters per second. Okay, erase it, scratch it out, whatever. It's gone forever. So now we do our x component and our y component. We say the initial momentum is 0 because it's at rest. 150 times 150, that's the x component of the first one, plus the second one is 100 times, what's the x component of the second one? How much of that 200 is x component? Jackson, how much of that 200 is x component? Yeah, except we're going to make it negative 173, right? How come we're making negative? Yeah, it's to the left. Good. Plus, mass of the third piece is 150. How did I know that? Yeah, 400 minus 150 minus 100 is 150. You guys okay solving for this? Get this number, combine them, take it over to the other side, divide by 150. If you need help with the algebra there, let me know. V3F is negative 34.53. Y component, here, I'm just going to go down here, guys, for the Y component. It's not number 5, it's still number 4. 0 initial momentum. Guys, just listen, please. 0 final momentum for object number 1, because it's all on the x-axis, and we're dealing with Y now. Plus 100 times the Y component here, which is negative 100. Negative because it's down. Plus the final mass, the mass of the third piece, times V3F. Solve for V3F. Hold on one second here. V3F Y component is 66.667. And now we just combine these, right? I won't finish this off, but I'll just show you what the vector diagram would look like. 34.53 and 66.667. And you do your Pythagorean theorem in the inverse tan function there. Good? All right. If you haven't finished 4 to 6, please finish those up for homework tonight.